So after discussing the initial 2 units from this particular course, which was initially with an introduction to an embedded system, and then we discussed about the different aspects of operating system in order to include that operating system into an embedded applications. Okay, so let's move ahead for discussion of the 3rd unit in this particular course of embedded system and operating system. And the title of that particular unit is Real Time System and RTOS, that is Real Time Operating System. Let's see what all the agenda that we have for the discussion. This particular session is going to be a very preliminary or introductory session in order to understand the basic concept of real-time system with couple of examples. The outcome after this particular session is you should be able to understand the concept of real-time system with some examples of it. So let's see what is there in the agenda. So today we are going to discuss about what is mean by real-time system, what is the significance of the system being designed as a real-time system, then what are the different analogy that we can build up for the real-time system with an example that we know, non-technical example, but that we know in a common day-to-day routine of it. Then we'll see what are the different types of this real-time systems, what are the typical example of this real-time system. There are a couple of misconceptions that many people do carry about this real-time system. We'll see this particular misconception in order not to get trapped into these misconceptions. Then we'll see what are the typical characteristics of this particular real-time system. Then we will have some inference or conclusion on the discussion based so far that we will be doing today. Okay, so let's move on to understanding very first aspect, like what is real-time system and what is its significance. So we have narrated the significance, or we know the real-time system is a category of an embedded systems. So when I say it's a category of embedded system, essentially this real-time system are basically meant for a single task, single function, which has got characteristics as single function, reactive, real-time, and tightly constraints. So when I'm saying it's a type of embedded system or category of embedded system, all the characterization that we did for embedded system equally gets applied to this real-time system. So what is new into it now? I would say the value added embedded system in the form of time, in the form of deadline of execution is referred as a real-time system. I repeat, the value addition that we can have in the embedded system in the form of deadlines or completion execution time, this particular system with an value addition of the time aspect is referred as an embedded systems. Now let's see formally what exactly it is being written in the literature in related with this particular real-time systems. So it is being written that a real-time system is any information processing system. When I say it's any information processing system, I refer to an application that we already know, which gets bound into the 3 C categories of it: control application, communicate application, and computing application. So I might refine it like a real-time system is any information system, either a control or communicate or compute oriented, which has to respond to externally generated input stimuli within a finite and specified period. Means here, if you carefully observe, the reactivity of the system is getting discussed in the form of real-time systems. Means when we know that most of the embedded systems, or around 90% of the embedded systems, are basically an interrupt driven. When I'm saying an interrupt driven, essentially they are mostly as an external interrupt driven. So when some interrupt is being generated, I can refer that as an externally generated input. Even some sensor might change the value. Depending on that, I might need that particular value to be taken as an input to my system. So the external generated input may be in any form of the case. So if my system is able to respond to that particular external generated input within a specified and finite amount of time, then that particular system is referred to be as a real-time system. Now, why this particular response happens to be there in finite and specified period? Because the output of the system might not be as expected if the system fails to respond to an external stimuli, or to a larger extent, even an internally generated events also. We can generalize it rather than only being referred to as an externally generated input. I can say that even internally generated events also, the response time, reactivity of the system has to be within a finite and specified period of it. And obviously, as we discussed, that the resultant output definitely going to be valued, or resultant output definitely going to have some meaning if that particular reactivity is being found into the finite and specified period. Okay, so formally, if I wish to define, or if I wish to further elaborate the concept of real-time system, then I would say that the correctness of the system depends not only on the logical result, but also the time it was delivered. And this is what most of the literature has given the definition of the real-time system. That real-time system is a category of an embedded system in which the output of the system is not only depends on the logical correctness of it, but also at a moment of time at which this output does take place. So when I'm saying and, I refer that as a logical and. Means if I want to make the output to be as invalid, or if I wish to have the output to be significant one, then I need to have that particular output not only as an in a logical correctness form, but also the moment of time at which this output occurs, that should be as it is being specified, or as it is being defined, or as it is being predicted while designing of the system itself. This is what this particular real-time systems are all about for it. I repeat, the output of the system not only depends on the logical correctness, but at a moment of time at which this output does take place. This is what the theoretically, or this is what the literary language for defining this particular real-time systems. So again, I can add up one statement onto it. Failure to respond within a specific time is as good as the wrong response. Failure to respond within a specific time is as bad as a wrong response. Means it is as good as not given a response itself. Means whenever you are supposed to design and develop an embedded system in which the execution timeline happens to be the most priority or most significant activity of the execution of the system or the output of the system, then that kind of systems are referred to be as a real-time system. Otherwise, as I said you earlier, real-time systems are the embedded systems. They are reactive. They are they are definitely a single function. They are tightly constrained in terms of their execution and in terms of their design environment. But along with this, they meet a specific deadline. Now, this particular specific deadline, should that be very small or what? Like, this is what we're going to discuss in the further part of this particular discussion. Okay. So at the moment, I just want you to understand what exactly this real-time system is all about. Okay, fine. Then if I if we discuss some common analogy that we know for the real-time system, which are very interesting examples, those we can find from the common our day-to-day life. The example number one is this particular diagram. If you see, then we have valid reason to understand whenever a rat wanted to catch up this particular piece of anything like cake or piece of butter, and if that piece of butter tends to get rolling over the surface, like these particular lines which are being drawn here, they represent that this particular piece of cake or butter is kept rolling, and this particular rat wanted to catch up that particular piece of this particular or food for this particular rat. Now, in order to meet with an output that rat should be able to catch up this particular food, what is the requirement? The requirement is that the moment at which the rat would catch up this particular food, the rate at which this rat would be flowing on the floor, or the rat would be running on the floor to catch up this food, should be synchronized or should be matching till the point this particular food gets rolled from this particular platform. Once it gets rolled on this particular platform, even though it catches up the things, it will not be of any use, because you might understand that beneath this particular platform, there might be some caveats where the rat will not be able to have this particular food once again, once it get fall out of this particular platform. Now, what is significant into it? Timing. Timing of the operation that this rat has to catch up this is extremely important. Once you miss the time, then it's of no use even making an attempt of it, right? The second example, which is very famous as we know it's from the childhood, the story of this particular tortoise, right? What does it indicate? It indicates that going steady even win the race, isn't it? So this signifies that the real-time systems, or the systems, once we need to meet with some kind of deadlines. So these particular deadlines are not necessarily to be a very small deadline, or the systems are not necessarily to be a faster system. This is what we get to know from this particular second diagram. The third diagram is still more interesting one. Like whenever you want to catch a rat, when you want to catch this particular rat, then we have a specific system that we call them clank, right? So if you want to catch this particular rat, then we have some food which is kept into this particular clank. What is from the operation point of view, what is important? It is important that once the rat goes inside this cage, inside this particular clank, the door of this particular clank should be closed off, so that this particular rat would not be getting chance to escape out of this particular clank. So is it not the timing is important? Means you can have the sensory system, you can estimate the amount of time in which this particular rat can just escape, can run the maximum speed, and within which you will have to close this particular door of this particular clank. Is it not a design aspect? And is it not like once this particular door of the clank is closed and rat ran away? Means door of the clank is closed, that means has that particular system got the functionality? Yes. Has that system got the functionality in terms of the correct sense? Yes, because the functionality of the system is to close down this particular door of the clank. But is it of any use? Rat has already been escaped out of this clank. So even though the logical correctness is being observed into the system, unless and until that logical correctness observed at the very appropriate time, that particular system will not be referred to be as a real-time system. That is what, this is a very famous analogy that is being found into this analogy to this particular real-time system, where the output of the function or the functionality as well as the timing of that functionality is equally matters. There is an and between it. There's a logical and in between it. Functionality of the output as well as logical correctness and the timing of that particular output taking place is equally important. And that's what it is being there into the logical and style of it. The next diagram is again going to be very interesting, which again indicates the timing of an operation. If you just want to hit this particular mosquito with a plant, then irrespective of n number of times that you hit this particular plant for this hitting of the mosquito, unless and until the timing is not being matched, you will not be able to put up the operations of it. I mean, this particular 4 diagrams or 4 analogy that we find into the real-time system necessarily dictate the basic characteristics of this particular real-time systems. Okay. And we are supposed to design the system in a real-time way by meeting up these kind of characteristics. Getting it? So this particular first diagram, A diagram, that indicates that you need to have a very fast and reactive in order to do the operation within a specific time. The second diagram that indicates that you have to keep going. It's not like the time deadlines are so urgent, but you have to keep going for it, right? So it indicates that the deadlines are not necessarily to be a very short one. Okay. The third one, as we understand that correctness and the output of that has the output of logical correctness and the timing is equally important for it. And fourth one, that we understand the timing at which the synchronous activity, the different activities are expected to be synchronized is equally important in order to be able to design these real-time systems. So these are the 4 analogies that you can remember in order to ease out and for understanding of this particular concept of real-time system. Okay, so going ahead, you can see that what are the different types of real-time system. Now, basically, types of real-time systems are derived from the resultant output behavior. Like the basis for classification of the systems are basically what kind of output that happens and what happens if that particular output doesn't met with the functionality, doesn't met with the timing that is being specified during your design time. Means, as I said you, that logical correctness and the timing at which that particular output happens, there is an and condition, right? So you can have, for this and condition, you can definitely have the variations. Being the two variable, I can have the 4 options available, isn't it? So based on this, like the correctness has happened, but that has not happened in a specific time which is being defined for it. Then in that particular case, what would be the resultant output behavior? And that is what going to decide, or what that is what being put up as a basis for defining, or that is what being put up as a basis for finding out the different types of real-time systems. Okay, so we'll move ahead with the first type of real-time system, in which if a system does not meet a deadline, then the output of the system would generate some kind of catastrophic events. Okay, so you can see that the hard real-time systems as a first category, as it gets defined as system where it is imperative that response occurs within the required deadline. If response doesn't occur in a required deadline, then the resultant functionality will not be of any use. And the better example that is being given for this is flight control systems. If something goes wrong in the flight control system, then I think it is known to everyone what are the consequences that would take place for it, isn't it? So even in many of the literature, it is being defined that if a deadline is being missed, and if that missing of the deadline is going to result a threat to a human life, please mark my words, if missing of the deadline of a functionality, if there arises a threat to a human life, then that kind of systems are referred to be as a hard real-time systems, where missing of the deadline is not at all tolerable. That is what the hard word is being used here as a definition, or the type of this real-time system called as a hard real-time systems, isn't it? There are many examples that we can discuss it even further part of it. But any example that is being, as we know the systems where the deadline misses and it gives the threat to a human life, then that is referred to as a hard real-time systems. I would say the vehicle braking system, where the ECU computes the braking and unbraking forces, like for example in ABS. Okay, so once it computes the braking forces, unless that braking forces is not being communicated properly to the brake drums, the brakes will not be applied, the debraking force will not be applied in a proper way by which the vehicle would get stopped. And if it is not getting stopped, then we know that there happens to be a catastrophe where the total failure of system will be there. So even though the brakes are getting applied, has that brake got applied within a specific time? If that is not, then there is a threat to a human life, isn't it? So that kind of examples or that kind of systems are referred to as in hard real-time systems. If I move further for the category of soft real-time systems, then where missing of the deadline will degrade the performance of the system at the most. Missing of the deadline will degrade the performance of the system, but it will not lead to the total failure of the system, or it will not lead to any threat to a human being. Always gives a very famous and interesting example for this, though it is being written data acquisition system. This is also an example of soft real-time system where we understand being missed few of the samples to be acquisized out of the total sample, the system would continue in its operation for acquisizing the sample, and whatsoever the sample that it might get acquisized, whatever the sample that it might get correct, it would continue with its functionality. Only the resultant output will be degraded in terms of its performance. But there will not be like the system failure or stoppage. That kind of things will not be there at all. One more example which I always gives in the class of this, that the video decoding system or encoding and decoding of the video. Let's say you are seeing a match, cricket match, okay, where the Kohli hits the ball, and it is expected, like depending on the standard of encoding, 30 frames per second are expected to be decoded, encoded and decoded at your receiving device, isn't it? So if 30 frames per second, that means there happens to be a time deadline. In 1 second, 30 frames should be decoded anyway, in order to see the pleasant viewing experience of that particular streamed video. If something goes wrong and 30 frames could not be decoded out of that particular 1 second, what it will result? It will result into the unpleasant viewing experience. And because of this unpleasant viewing experience, there is no threat to a human life. No one will going to do something very bad if he or she cannot see the complete frames in a 30 frames in a 1 second, isn't it? So that kind of systems where the degraded performance is being found after missing a deadline is referred as an soft real-time systems. Okay. The next category happens to be real-time systems, where these are the hard real-time systems whose response times are very short. Okay. In the first category of hard real-time system, we haven't talked about any response time of it. Okay. So this response time may be like, for example, maybe few microsecond, nanosecond, till it might be till minutes or hours also. Whatever it is being defined, within that the output should take place. And if output doesn't take place within that time, then it is said to be as a hard real-time system. But if that particular deadline, if that happens to be, or the response time happens to be very short, if response time happens to be very short, then I do have the further categorization of the system, real-time system, called as a real-time system. We have basically only two categories: hard real-time system and soft real-time systems. Okay, so here this particular real-time system is one more derived category where it is a hard system, hard real-time system, and response time is also going to be very short. An example that is being narrated here is a missile guidance system. Isn't it? Whenever you have got the weapon launched onto the aircraft, then the avionic control that is going to dispatch that particular weapon to hit the target. You understand what kind of timings and what kind of accuracy and precision that might be needed into the control system which controls this particular missile guidance systems, isn't it? And in that particular case, the reaction time, because the speed with which the planes would be moving on, the speed with which the aerial vehicles would be moving on, that would be too high, too heavy, too speedy, and because of which the timing that it needs to adhere for generation of the control signals and generation of the actuating signals in order to hit the missile to the opponent's target plane, that is even going to be a very short, very small of it. So this is one type that is being referred to be as a real-time system. And last type that is being referred to be as a firm real-time system. Whenever I'm saying it's a firm, okay, firm, this particular firm word, we can take it from the firmware, where it's a combination of software and hardware, isn't it? Similarly, I can remember that this firm real-time system is where it's a combination of hard real-time system and soft real-time system. What does it mean? So in your systems, there are a couple of deadlines which would happens to be hard deadlines, which would happens to be, or sometimes some deadlines happens to be in soft real-time systems. That means the system, this particular system will not generate any catastrophes. It is a soft real-time system, but in which there are no benefit from delayed delivery of the service. That means some deadlines are expected to meet within some deadline, or some task expected to meet within some deadline, and some tasks can continue their operation without meeting the deadline also. Getting it? And that is what we call, it's a combination of hard and soft real-time systems. Okay, so the if we see the very complex embedded systems like avionic controls and all, that falls into the hard real-time system. Most of the consumer electronics or the different systems that we do use day-to-day life, that happens to be there in soft real-time systems, or then there are many in the soft or firm real-time systems. Okay, so it is based on, first of all, we need to understand what kind of category of real-time systems we are subjected to design. Then only there is a point in finding out the granularity of the task, defining the task deadline, trying to meet that particular task deadline with the help of different algorithms, different software architectures that already we have discussed with, right? So all this particular thing that is very significant, and that is what type of real-time systems are known, expected to be known to us. Okay. Fine. So next we'll see some couple of more examples for this. Like for example, number one is automated teller machine, which is a categorization of the soft real-time system, where it is being explained like missing even many deadlines will not lead to catastrophic failures, only degraded performance. What does it mean? In the ATM machine, if you are not able to enter the password successfully within some allotted time, then it will give you a second chance, third chance, and fourth chance. So it will just degrade the performance. Okay, but no catastrophe would occur for it. It's as simple as this. The second example that says that embedded navigation controller for autonomous robot weed killer. Okay, so that referred to be as a firm real-time system where missing critical navigation deadlines that would cause the robot to veer hopelessly out of control and damage the crops. This is what referred to be as a firm, where some guidelines are being there for the hard, some are being there for the soft. The next application that you can see as an avionic weapons delivery system, in which pressing a button launches an air-to-air missile, as we saw it, right? So it's an hard, because missing the deadline to launch the missile within a specified time after pressing the button can cause the target to be missed, and being missed the target, which will result into some kind of catastrophe, which is a total failure of the system, isn't it? So these are some typical examples which are being there in and around in order to design or in order to exemplify as a real-time systems. Okay. After understanding or getting few of the examples to be known, we can move ahead. Okay. Before we move ahead, let me tell you that the literature, or I'm very fond of a book that gives us a very detailed literature about the conceptualization of real-time system. And that book is being referred here as Real-Time System Design and Principle by, or Design and Analysis by Philip Laplante. So this is a book which is, according to me, a very sound book which give us most of the concept of real-time systems. Okay, because real-time system design happens to be involved with more mathematical equations and even the control algorithms and theory also. Okay, in the next lecture we are going to discuss about all these particular issues and the basic principles and the approaches for design of real-time system. Okay, so in this session, primary objective is to understand or just get concept of the real-time systems. Fine. Then there are a couple of common misconceptions that keeps on building around the real-time systems. So what are these misconceptions? That we'll just refer it at once, and we'll keep on discussing these misconceptions throughout this particular unit. Okay, fine. So number one misconception is real-time systems are synonymous with the fast systems. This is completely, or this is merely a misconception as I narrated. The diagram B for the common analogy that I have given for the tortoise, that was a resemblance to this particular misconception. It's not essentially to be as a fast system. Even your deadline happens to be minutes, hours, day, there, even by definition, those systems are also referred to be as in real-time systems. Okay. Then rate monotonic analysis has solved the real-time problem. In the early days when these particular real-time systems got designed, most of the designers rather, have relied heavily onto the scheduling algorithm that we call rate monotonic analysis. And this particular rate monotonic analysis allows the designer to schedule the tasks which have frequently occurred. And as these tasks are frequently occurred, there was valid reason to get understood that these tasks are of a high priority. And that is what this rate, where occurrence of an event, occurrence of the task is in high order. And if that particular occurrence of the task happens to be with a continuous pattern, with a repeating pattern, then I can call that to be that as a monotonic, isn't it? That is what this rate monotonic analysis for the scheduling policies that has solved the problem in the past for real-time systems, because unless and until task is not being of urgent and important, that is not expected to be scheduled. Okay, so it's not the case that this algorithm has not been solved the real-time problem. Okay, so this particular rate monotonic analysis has solved the problem, but this is not the algorithm which solves the problem. Getting it? So there are different algorithms, there are different alternatives, those are being available. And one of the alternatives that we have already seen when we discussed little about MUCOS2, which is a scheduler which has got built up on a policy of high priority and ready to run tasks that must be running. So again, based on the static priority encoding, I can keep on doing the prioritization of the task for scheduling purpose of it. Okay, but this particular rate monotonic analysis is not the only solution for the real-time problem. This is what people had a misconception that has solved the real-time problem completely. So that is not the case. Okay, that is one of the tool that has been appreciated a lot, but that is not the tool. There are universal, widely accepted methodologies for real-time specifications and design. This is what we are discussing misconception, right? So for everything that we can say that not. No, there are no universal available accepted methodologies. Why? Because as I said you that for embedded system design, there are no rules as such. There are a couple of guidelines. And these guidelines would keep on changing according to the different categories that the designer would experience for design of embedded systems. Because every system is different by its specification, every system is different by its functionality, isn't it? There are so many variations and variances even into the functionality and specifications. And that is what there are no common, there are no available for this universal or widely accepted methodologies. Okay, if someone says that it's an universal available methodology available, then that is a misconception. Or it is being said like there is no need to build the real-time operating system because commercial products exist. This is again happens to be a misconception, or we call that as a myth. Okay, so many times you might need to design your own operating system in order to meet the deadline, in order to meet the specification and requirement of an application. And mind you that MuCOS 2 have arisen, or MuCOS 2 got in existence because of this fact only. Okay, even though during the MuCOS 2 there were so many operating systems which were available commercially, but none of the operating system could really suffice the requirement of an application. And in that particular case, why not to write our own operating system which will cater the demand of an application? With that thought, Jean Labrosse and his team at McRae Semiconductor started designing an OS, and we are studying that OS in the form of Micro C OS 2 MuCOS 2. Getting my point? Microcontrollers operating system 2. That's MuCOS 2. Fine. So there happens to be a need for design of operating system. Okay, so don't just rely on whatever the commercial products available for your design purposes. You might need to go into the design of real-time operating systems even. Last misconception that happens to be study of real-time system is mostly about the scheduling theory. This is again a misconception. It's not only the scheduling theory that's going to build and design the real-time systems. Along with the scheduling theory, I might need to be very strong in inter-process communication. I might need to be very strong in protecting the data. I might need to be very strong in communicating the data to each other, inter-process communication, inter-process synchronization. All the allied services which are being there along with scheduling is equally important in order to meet the deadline. So that is what, if someone says that it's a study of real-time system is mostly around scheduling theory, then again it becomes to be as a misconception for it. Okay, so these are few misconceptions that people carry, and I'm discussing this misconception so that we could get rid of this misconception. We should not get trapped into this misconception. So we will have our minds and open in order to adopt the changes which keeps on happening into the design of these real-time systems. Getting my point? So this is what expected to be known at this particular time. Then characteristics of the real-time systems, I can quickly go through these characteristics because already these characteristics have been discussed during the embedded systems also. Large and complex, like very few of hundreds of the lines of the assembler or few millions of the lines of this AD estimated for space station freedom. So, I mean, these particular real-time systems might be varying from few of the lines to few hundred or few millions of the line of code. Okay, so complexity may be small, complexity may be large of it. Then concurrent control of separate system component. This is very interesting and important. As I say, that device operates in parallel in the real world, obviously, as we have seen it, right? Better to model this parallelism by concurrent entities in the program. And this is what exactly we are trying to design real-time systems by having a concurrent programming model of it. That's what we want most of our tasks to be there in a ready state. And among the ready tasks which has got high priority would be the scheduling one. So underlying algorithm or underlying mechanism of executing an application for MuCOS 2 is basically a concurrent mode of execution. And that is, as I said you, as a trade-off between sequential and parallelism. It leads to more towards the parallelism, and it gives you more advantage which could attend out of the parallel execution scenario, isn't it? So concurrency, that we are seeing it in the applications. Then facilities to interact with the special purpose hardware, obviously that has to be there as a characteristics of embedded system, this real-time systems. Extremely reliable and safe. So being this embedded system, the control environment in which they operate, failure to control can result in a loss of life or damage to environment or economic loss. That is what they have to be very reliable, as well as even being occurred some fault, it should not give any threat to a human life, isn't it? So loss of life as well as damage to environment and economic loss, that is expected to be under control. That is what it is, extreme reliability and safe, which is a general characteristics of embedded systems also. Okay, fine. And last one is ice on the, it is top requirement, top characteristics. Okay, I would say it's a cherry on the cake, where it should give me the guaranteed response time, where we need to be able to predict and predict with the confidence the worst case response time of the system. So efficiency is important, but getting predicted is more essential than having an efficiency. And that is what the real-time systems have got synonymous of deterministic systems and highly predicted systems, where the worst case response time is being already known. And that is what you are able to predict this particular system. A simple rule that I can apply is, if I can have the simple algebraic equation by which I can just have the different services estimation, I can do it very accurately. Then I can say that I am getting the system to be designed in the most predicted environment or in a predicted operations, predicted mode of its functionality. And that is what referred to be as a real-time systems. Okay. Some common examples still we are supposed to find out is like a simple fluid control system. I think from the diagram itself, you could get to know like what kind of systems is this all about. Okay. I left out to you to just see this particular diagram because already you know what is real-time system, and we are quoting this as an example of this real-time system. Getting it? The second example that we can see is a grain roasting system, where we understand that if I want to roast the grain, any grain into the furnace, the temperature control is highest important point, right? So unless and until that particular from the bin, the grain is getting poured onto this particular furnace, right? The fuel tank is going to supply this particular fuel for this particular furnace. Okay, so there is a control mechanism, and control mechanism demands that the rate at which you are giving this particular fuel, or rate at which you are just making this particular grains to just come out of this particular bean, that rate has to be controlled in a way where this particular grain should be roasted to an required level. It should not be over roasted. It should not be an under roasted. So that also becomes a case of the real-time system, soft real-time systems, obviously. Then this particular widget packaging system is also being known to us, like conveyor belt, the timing and everything is what being known to us, right? So in the next part of this, we will discuss this particular example as, and we'll take this particular example for the design environment of this real-time system. Okay, because most of us understand these particular systems very well, being a common system. Okay, and we can understand that this particular switch, or there are many sensors and actuators which are being required in order to synchronize the activity as on when it is being required to meet the functionality, isn't it? So there is no point in just making this particular switch open by which this particular widget would fall into the box if box is not being found on right. Means everything is being based on the timing of its operations, and these timing operations are basically expected to be captured for this particular real-time systems. Fine. Then this is what I planned for the introduction to real-time systems. Okay, so maybe like reference books which I told you, the real-time system design and analysis by Philips Laplante is a very famous book that many of the designers are making use for the references. Second book is real-time systems, where the more mathematical oriented treatments are being given, which is from the author called this Jane Liu. Okay, we are in the next in this particular next discussion, what we are going to understand is how does this real-time systems are getting modeled. Okay, what are the different design methods? Like if the task happens to be a periodic task, sporadic task, then how this particular real-time system design changes? What are the different issues involved into it? And in order to get out of this particular issue, to address this particular issue very aptly, What are the different approaches that one need to find out for this? Okay, so that's it. This is the discussion that I planned it for introduction to the real-time systems. Okay, so I thank you for attending this particular session. Thank you.